a very brief introduction. So the second lecture of our open lecture of our guest professor, Vasily Tverkiewicz from Auckland University. So Faculty of Physics was so kind that invited him for 2 months, and we can learn from him about quantum optics, quantum magnonics, and in general principles. And today he has a special lecture where he will be talking about entanglement. And if I understood it right, we even will see some real-time demonstration that maybe we will see the difference between classical physics and
we'll try.
Quantum.
We'll try. Okay. So, because you see, the correct way to settle physical disputes is to do physical experiment, not hit each other, even with arguments. So, let me start with a very small demonstration. So I have a deck of cards. I draw one card randomly. I shuffle it, so I don't know which card I took. It's a random card. It has 50% probability of being red and 50% probability of being black. So I look at it, and it is red. Okay, let me ask you one very stupid question. Was the card red before I look at it?
Yes.
Yes? Are you sure?
Yeah.
Yeah? Can you prove it?
No.
Can you make experiment? This is, yeah, like, of course it was red. What else could it be? Come on, this is stupid. But please give me experimental proof that card was red before I look at it. How can we do this? This is the same as looking at this one, because there is slight correlation between them. And measuring all of them, well, measuring is the same as looking, but in quantum physics. Looking at all of them, you know which card it is here. So, but can you somehow prove that it is red? It's not red and black at the same time and chooses its color at the moment I reveal it. Well, this is a very difficult question. It's not that easy to do as you think. And today, we will try to settle this question experimentally. So first, I will introduce, well, of course we will settle this question not with this card. Unfortunately, there are a lot of experiments that we cannot do with classical card. We will do this with quantum cards or qubits. So first I will explain what qubits are and how to draw a random qubit card. And here I am talking, of course, about superposition states. Then I will make a slight modification of this simple experiment that makes everything much worse. So much worse that Einstein did not believe quantum mechanics and criticized it for many years. And then we will talk how we can actually find out if the card has a color before we look at it. And we will test it with quantum computers. So let's start today. So quantum cards or quantum analog of cards are two-level systems. The simplest example of two-level system is electron spin, which we all know can be either spin up and spin down. There are two states. So this is our red card and our black card. And instead of electron spin, we can choose any other two-level quantum systems. They behave the same. So such two-level quantum system, independent of realization, are now usually called qubits from quantum bit. So qubit is quantum bit. And spin-up state, well, if we are not talking about spin that has direction, usually is denoted 0, spin down is 1. So 0 is the red card, 1 is the black card. So for a qubit, as we know from quantum mechanics, so these are the basis states. And quantum system can also be in superposition of these basis states. So in addition to these two very clear classical states that we can understand as red and black card, we can form infinitely many other states. For example, state minus, which mathematically is written as 0 minus 1, can be represented like this. And this yellow sphere represents what is called in quantum physics Bloch sphere. So any state of a qubit can be shown as a certain direction on a sphere. So this is state minus, this is state plus. If we are talking about real spins, these states minus and plus have very clear physical meaning. So state 0 and 1, our red and black cards, they correspond to spin directed either up or down. And we can measure this physical direction in something like Stern-Gerlach experiment. So then spins states minus and plus will correspond to spin directed left and right, so just along a different axis. So how do we know that these superposition states are real? How can we prove that they are real, that it's like if spin or qubit is in such state that this is not just like a card being randomly drawn and has red or black color, but it has a color before I look at it. With qubits, we say that qubit in this state, it does not have a color before we look at it. So we choose this color at the moment of our measurement, or when I reveal this card. So how can we know this? Well, we can do experiments, and we can do experiments and prove this experimentally. And we can do this because in quantum worlds, we know how to rotate qubits, how to rotate this position of a qubit on the Bloch sphere. For example, if I apply a rotation, air-wire rotation, such rotations are called quantum gates. If I apply a rotation by 90 degrees, then my initial state 0 and 1 will turn into state minus and plus. So this rotation, they are called quantum gates. This particular rotation, it corresponds geometrically to rotation about axis y that goes perpendicular to the screen. So this quantum gate is called Ry, and rotation is by minus 90 degrees. Minus because I rotate in counterclockwise direction here. Okay, so what is important? What is important that while we rotate this qubit, we do not look at them, we do not measure them. So that would mean, like if with analogy with cards, that would mean that I can take card and I can do something, change its states without looking at it, without measuring it. And using these qubits, we can perform some experiments in real quantum computing. So here is a small graphical description of a quantum program, so sequence of actions we do with qubit. So such graphical description is called quantum circuit diagram. So it shows line for a qubit, for one or more qubits, and here I put stuff that I do to this qubit. So every quantum program starts with qubit in state 0. So this is the same as our memory in our classical computer starts when we switch computer on, it starts with state 0. Then I apply this rotation gate. So I rotate this qubit by 90 degrees. And after that, this symbol, it corresponds to me measuring the qubit. This is the same as I take and reveal the card, and I look at its color. So just here I am looking at the color of my quantum qubit card. And now in this histogram, I show results of execution of this program on a real quantum computer. So this is not a drawing, this is not a simulation. I send this program to quantum computer developed by IBM, which is located somewhere, I suppose, in America. Well, and this quantum computer is formed by, is kept in millikelvin temperature, it's cooled down at millikelvin temperatures, and it has about 100 or 150 qubits, which have the form of very small superconducting loops with Josephson junction. And these superconducting qubits, they act exactly as we discussed, as these quantum cards, with two basis states, and we can rotate them, and we can put them in superposition. So what we see on these results of execution, and at the end of the lecture, I will try to demonstrate you live execution of program on a quantum computer. So what we see here, so after I run this program, I run it 1,000 times to get enough statistics. I see that about half of the time, my qubit ends up be in state 0. So half of the time, so I draw this random card 1,000 times. Half of the time the card is red, half of the time the card is black. So this is how we can do this. Of course, this experiment does not prove that superposition states are real, because I can do exactly the same with classical cards. I can draw thousands of them, and half of the time they will be red, half of the time they will be black. So how can we prove that superposition is real? Well, with a slight modification of experiment. Here I show two very similar programs. Again, we start with qubit in the state 0. Then I rotate qubit by 90 degrees, and then I look at it. Then I rotate it again and look at it again. The second program is very similar. I rotate it once, I rotate it twice, but the only difference is that between these two rotations, I don't look at the qubit. So first time I rotate the qubit 90 degrees, I look at it. And then I rotate it again. And when I look at this qubit, if quantum physics is right, qubit cannot remain in superposition state. So here when qubit chooses its color, it chooses whether it's red or black. And the second rotation starts from this red or black situation, so we go back to the superposition. But with the second program, I do not look at the qubit in between, so it may remain in superposition state. So I have qubit initially in state 0, I rotate it 90 degrees, then I rotate it again 90 degrees. So qubit should end up in state 1. And here are the execution results. Here is the same as before. It's random drawing of a card. So it's like a quantum coin toss, 50 by 50. This case, well, qubit in more than 99% of cases, 1% is experimental error. More than 99% cases, qubit ends in the state 1. So this experiment proves that superposition of quantum states is real. Very simple experiment, you can do it yourself. The only difference is that here we look at the qubit and here we don't look at the qubit. So it proves that measuring quantum system, looking at the quantum system changes itself. It proves that when we don't measure quantum system, it may remain in superposition state, proves that superposition states are real. Okay, so this is very fine and interesting. So, but this fact that qubits can be in superposition in 0 and 1 states, it does not change our understanding of reality in any significant ways. Okay, qubit is slightly more complicated, slightly more complex than just a card, because card can be red and black, that's all. Qubit can be in superposition, but still, each qubit and every moment of execution of this program, qubit is in a particular state. It can be 0 and 1, it can be superposition state, but there is a definite state, and at every moment, if I know the state, I can predict everything what is going on with qubit. What will be the result of measurement, even if it's probabilistic, what is the result of application of any gate, and that's all. So that's what we have when we have just one qubit. But let me show you a slight modification of my experiment. So here I have two cards. I chose two cards, one red and one black. So I toss them. I want to form quantum superposition of these two states. So I toss them. I put one card here and another card over there. They are far away. They cannot interact. Yet their states, well, they are correlated. If this card is red, that one must be black. If this one is black, that one must be red. We can do this with classical cards, and we can do this with quantum cards. But there is one big difference between what classical understanding tells us and what quantum theory predicts. In classical case, So these two possibilities, red here and black there, or black and red there. So these two possibilities simply describe our knowledge, or lack of knowledge, our ignorance about state of the system. Classically, each card has a color. So this is either black or red, this card. I just don't know it. But it has a particular color. So this is what we used to think about, not just card, but about everything that exists in the universe. This is what is called physical realism. But quantum theory tells different story. Quantum theory tells that these two possibilities, red here, black there, and black here, red there, they exist at the same time. And that leads to a lot of problems. For example, what happens if I reveal this card, if I measure this card? The distance between two cards may be very, very large, such that even light travels between them like for hours. But at the moment when I look at this card and see that it is black, I can predict that that card must be right. So before this measurement, quantum theory tells there is nothing in the world that can predict what will happen if you measure this card, if you look at this card. It's a random choice. It's a random thing. But here I do something. Say I send that card to Alpha Centauri. It's 4 light years away. So I look at this card. I see that it is black. And at this very moment, not 4 years later, so that's how much time, light takes to go to Alpha Centauri, but at the very this moment, I can immediately predict what will be the result of measurement of this card. This contradicts our understanding of how things work. This contradicts like relativity argument in this world. And this is and this is why Einstein criticized quantum theory for many years. Let's look at this state a little bit more. So in this state, according to quantum physics, these two possibilities, red and black and red, they exist at the same time. And that means that if I want to use this nice Bloch sphere description of these two cards or these two qubits, well, I can draw this combination in 0 and 1 for one part of superposition. And I can draw similar description for other part of superposition. But quantum theory tells us that these two possibilities exist at the same time. So it does make sense to consider them separately. They do not describe real state. Like picture like this, two separate possibilities, this is what classical physics tells. Red here and black there, like this. Or black here, red there. We just don't know. Quantum physics tells that these two possibilities exist together. So I have to consider them together. So I can draw the state of the system using this double-sided arrow. So blue arrow corresponds to one qubit, green arrow corresponds to another qubit or card. And if blue arrow chooses this position, if blue qubit chooses this position out of hat, green qubit somehow also chooses the same position even if it is light years away. If blue qubit chooses, or we measure this blue qubit and we see that if it is in out of tail position, then green qubit also must be in out of tail positions. So these two states, the two qubits in such state, which is called entangled state, they form inseparable entity. We cannot separate them. I can draw both of them on this Bloch sphere using this double-sided arrow notation. But if you try to describe state of one qubit, you cannot do it, because state of one qubit depends intrinsically on state of the other. So it's a type of a system when I can describe the whole system, either with mathematical formula or with graphical depiction, but I cannot describe what is the state of one qubit, because one qubit or card is neither red nor black, nor it is even in superposition of red and black. Because if it is in superposition, then whatever, it does matter. When I look at it, I will have exactly the same 50% probability of seeing red and black. But in this state, if I see this card red, that one immediately becomes black, and so on. So, yeah, and when we measure this, this entangled state of two qubits, they instantaneously choose either one combination or another. Okay, so we cannot use this instantaneous wave function collapse to get any communication, to communicate between us and Alpha Centauri. Why? Because we cannot decide which side, we cannot choose which side this collapse will go on. So we get some knowledge, but we cannot use it for communication. If we could choose that, okay, I will measure blue qubit and I will go this side, well, then I can send some information. But we choose this split is chosen randomly. So we cannot use this to send information faster than light. So in principle, there is no like hard violation of relativity. We cannot send information faster than light. We cannot go back in time because of this. But it's still unacceptable from conceptual point of view. How this may happen, how it may happen that I do something here and immediately something changes for light years away. So this is why Einstein criticized quantum mechanics for many years. And one of the most, well, the most famous critical work was published in 1935. And it was published in co-authorship with Podolsky and Rosen. And right now we know this phenomenon related to this effect as EPR paradox. EPR, it stands, it's abbreviation of the first letters of authors of this paper. And in this paper, authors criticize quantum mechanics, arguing that it is incompatible with local realism. What does local realism mean? So locality means that nothing can travel faster than speed of light. So, or cause cannot move faster than speed of light. So if I do something to my card here, then whatever I do to one card can influence the other card only with some time delay. So this is locality. And realism means that properties of objects exist independently of our minds or our measurement. More precisely, Einstein argued that in this experiment, when I reveal one card, and I can predict with certainty color of the other card, that okay, I see that that card is black, I can predict immediately that card is red. So the fact that I can predict this property with certainty, that means that there must be something in that this property is element of reality. It's not something that we just come up with. So there must be something in reality that keeps this property like fixed in red color. And complete theory must have these elements of reality in itself. And quantum mechanics does not have such elements of reality. And therefore, Einstein criticized quantum mechanics that it is incomplete and, well, it should be changed. So Einstein did not say that quantum mechanics leads to some wrong predictions. All predictions, all experiments explained by quantum mechanics, well, quantum mechanics does an excellent job. But in Einstein's point of view, quantum mechanics was just an efficient mathematical tool. Similarly to how we use probability theory in classical world. For example, if I have a dice and I roll it, and I say the dice has 1/6 chance of land on any of its edges, I don't mean that motion of dice is random. Motion of dice is governed by Newton's laws. It's just this probability theory we are using to describe this motion is our way to deal with very complex processes, unknown initial conditions, and that's all. So maybe quantum mechanics is the same effective tool. Maybe it's just a convenient way to simplify calculation. And maybe there is some deeper theory, some theories that has some so-called hidden variables. So in these hidden variables will allow us to predict that color of this card is red without this instantaneous wave function collapse. Okay, so can we design an experiment that will prove one way or another? That will show that, okay, yeah, there is some hidden variables and quantum bits behaves as classical cards. Or otherwise, that we, that quantum cards are very different and they behave exactly as predicted by quantum theory. So to do this, let's do this. Let's perform so-called Bell test of our reality. Let's find out what our reality is, whether properties of objects are real or not. It's one important comment here. So classical EPR argument is based on two properties, locality and realism. So locality is that nothing can travel faster than speed of light. Realism is that like properties we are talking about, they are real, objective, and color of a card does not appear at the moment of measurement. In quantum computers that we will be using, qubits are very close to each other. Time of light travel between two qubits is very small. So we cannot check locality in quantum computers. For that, you need to work with photons and have several millions in funding. But we can check reality. We can check whether property is correct or not. So this is not exactly the work for which people received Nobel Prize several years ago, but at least it is half of it, and everyone can do it for free. So what we need to do to perform this Bell test, there are several important things. So first, we need to understand how we can generate these entangled states. But like not with cards that I can kind of like generate this, but how can we generate such state when it's 0 and 1, and here is 1 over 0, and two possibilities exist at the same time. So how we can do this in quantum computers? Even more difficult part is this one. We need to find some observable difference between classical descriptions that we just don't know and prediction of quantum physics. And this turns out to be much more difficult than it seems because, okay, mathematical description is different. But when we try to describe outcomes of experiment, very often it's like what classical theory predicts with classical ignorance is the same result as quantum theory predicts with quantum entanglement. Okay, so once we will do that, we will design program and run it on a quantum computer. We'll see how it will go. So let's start with generation of entangled state. So to generate such entangled state between two qubits, we need a new quantum gate. Quantum gate in which these two qubits may interact. And the gate that does the job is so-called C-node, control node gate. So here I already have two qubits because I need two quantum cards to test this reality. One qubit is control, another target qubit. And this C-node gates, it flips target qubit. It changes it from 0 to 1 or from 1 to 0. But it does this only when control qubit is in state 1. When control qubit is in state 0, this gate does nothing. So let's see what happens in simple cases. So if control qubit is 0, like this target qubit is 0, so this is input state 0, 0, this control node gate does nothing, state remains 0, 0. Both qubits are in state 0. What happens when we flip target qubit, so control qubit? So now control qubit in state 1 initially, target qubit still in state 0. So here this gate will be activated because control qubit is in state 1 and target qubit will also flip. So both qubits will end up in state 1. What is important, the same as with usual rotation of a single qubit, then all this is done without measuring the qubit. So we do these manipulations without looking at quantum cards. So no collapse happens here. If we had any type of superposition, it will survive. That's not very easy to design such case, but people did this, so we have them right now. Okay, so these are the simple cases. But what happens if control qubit was initially in superposition state, was initially in state minus? Well, to understand this, well, we have to take into account that all quantum physics, and that means that all quantum gates as well, so is linear. So we can understand what happens for superposition state simply by looking separately at each term of superposition. So state minus is superposition of 0 and 1. So if here initial state is the state minus, the result of action will be superposition of results of action when input state is 0, 0 and input state is 1, 0. And we already know what are the states. So here, for this part of superposition, output state is 0, 0. For this part of superposition, output state is 1, 1. So this is how I can write, like, the result of control knot operation is superposition of such two states, 0, 0 and 1, 1. I can draw them graphically using my double-headed arrow notation. It's like this. It's a little bit different states than states with cards. State with card was like completely anti-correlated. Here's black, here's red. Here's red, here's black. This state, on the contrary, is completely correlated. So two qubits are either in 0 state, or two qubits are in state 1. So such state has also its own name. It's Bell state phi minus. And we can depict it with two arrows pointing in the same direction. I can give also a classical analogy of this state. This is the same as if I randomly draw, so I have two red and two black cards. I can shuffle them and randomly draw one pair. So now you know that both cards has the same color, but you don't know which. And this is like a classical state phi minus. Cards have color. You know that they have color. You don't know which. Quantum state. Well, quantum theory tells us different stories, that both these possibilities exist at the same time. Okay. So once we generated this one particular Bell state, we can modify it and we can generate other entangled state. How we can do this? Well, we can simply take and rotate one of the qubits. So we'll apply, after we have state like that, we can apply some rotation gate to one of the qubit and we can create any state we want. We can also test existence of such correlations in quantum computers. So here is very simple program. I rotated one qubit, I put it in state minus, then I apply C0 gate. I created this entangled state here, and then I measured both qubits. Here's the results of this very long bins. They correspond to two qubits in state 0, two qubits in state 1. And here very small is when we have experimental error. One is 0, another is 1, or vice versa. So we see, we can test that such correlations exist experimentally. Now, this does not prove that quantum entanglement is real. Because I can do the same experiment with classical cards. I simply draw randomly pair of cards of the same color. You will have exactly the same statistic. And that's the problem. It's like, okay, this is very interesting state, but you can do classically the same stuff. We need to find something that we cannot do with classical cards. And this is not that easy. So first, this problem, finding measurement that with result, which are impossible in classical world. So first time this problem was solved by John Bell in 1964. So he formulated certain restrictions between correlations of classical objects, of objects that such that classical system cannot overcome. And I will explain today a simplest version of it. The real math behind it is very, very complicated. We will consider the simplest version of it. And the main idea why that was possible by John Bell and impossible but everyone who tried before is the realization that qubit is slightly more than just red or black card. That qubit can be viewed from different positions. Look, here I have the state minus and state plus. I can look at them as before, that this is superposition of 0 and 1 state. So this is like point of view based on z-axis, because 0 and 1 states are states north and south pole of the Bloch sphere, so they are states along the axis. But I can also look at these states from perspective of x-axis. I can say, okay, this is state left and state right, so this state corresponds to some different property, like different projection, x projection of qubit. Making an analogy with our cards, I can say that, okay, this axis, z-axis, it describes color of the card. So we have, say, black or red cards. Other axis, x-axis, describe a different property of the card. It describes, say, its parity. So 10 is even number, ace is 1 or 11 is odd number. So we have different property. Again, we can have only two like pure states here, even and odd, but it's a different property. Now, when we have classical cards, you look at it and you say, okay, this is black card and this is even card. So you see both properties at the same time. With qubit, it's not like that. Because in qubit, when we look at the qubit, we change it. We saw this in experiment that I showed previously. When we look at qubit, we change, we destroy superposition. We destroy all quantum state and create new one. So every qubit can be measured only once. But we can choose, based on this picture, we can choose how we measure it, what property we look at. So it's like we have cards, but we can look only at the color of the card or parity of the card, but not do properties anymore. But still, this gives us a choice we can exploit to check whether qubits are real and whether these properties are real or not. Okay, so we will use this picture. We will use this picture that qubits have more than one property. They have color and they have parity. So how would quantum state, but so far we draw all quantum state only in this basis, in this basis 0, 1. So how does entangled state look like in X basis? How does it look if we pay attention to parity of our quantum card? So this is just a question of taking this formula and rewriting it in a different basis. So this formula was written in system of coordinates 0 and 1. We need to rewrite it using coordinates plus and minus. So it's different coordinates. So you can do this, and this is what you will see. So in 0 basis or color basis, I have 0, 0 and 1, 1 combinations. So both cards are red or both cards are black. In X parity basis, I have minus plus and plus minus. I have anti-correlations. So I can describe this state as the state of two cards having the same color and different parity. But neither color nor parity of each card is defined. Okay, so can I test this? Can I test like that in X basis our state will look like that? Yes, I can, but to do this, I need to measure this X projection of a qubit state. Now, there is a limitation. Current quantum computers can measure only vertical projection of the state, which is like this Z projection of the state. But we can use the fact that rotations that I showed previously, we can look at these rotations from two different points of view. we can look at this rotation either as rotation of qubit or as rotation of coordinate system, but in opposite direction, like this. These are two equal points of view, equally valid points of view, because what does matter is only the position of the qubit relative to the basis. So you see here qubit points down, so it corresponds to state 1. Here qubit points left, so it corresponds to state 1. It's the same result, so it does matter. What matters always with coordinate system is the position of a point or vector relative to coordinate system. You can measure, you can rotate vector or you can rotate coordinate system in the same, the effect is the same. So since our quantum computers can measure only in vertical polarization or only vertical component of the state, I need to first to rotate this x-axis to put it in vertical direction and then perform measurement. This will allow me to measure parity, another property of my qubit. So it's very simple. If I just put measurement like this, that means I am looking at z projection of the qubit, or I am looking at the color of my quantum card. If I first rotate qubit, put this rotation and then measure, so here I rotate coordinate system and measure. So here I am looking at qubit in x basis. I am looking at the parity of the qubit state. Okay. And so with this, we can test. So this is the same result as previously. This is what happens when we measure in z basis. So this quantum state phi plus. So we have perfect correlations. 2 zeros or 2 ones. Both cards are either red or black. This is what happens if we measure this qubit in x, both qubits in x basis. So we see first I rotate, then measure, rotate, then measure. And here we see complete anti-correlation. So one qubit is odd, another is even. They are always anti-correlated. We can also perform measurements in mixed basis. So here, I do not rotate first qubit. You see, I just measure it, but I rotate second qubit. So first qubit is measured in z basis, second measured in x basis. And in these cases, there is no correlation at all. There are absolutely random, cards drawn, and so on. And the same is this one. So we see we have very interesting correlations between qubits in one basis and another. But these correlations, well, I can achieve the same correlations in classical world with classical card, as I say. So this experiment can be explained by simply, okay, we draw two cards that have the same color and opposite parity, that's all. They will have correlation like this and correlation like this, and they will not be correlated in this cross basis. So what we need to do to make measurement or get a result impossible with classical cards, we need to change our state a little bit. We need to make states such that we will have correlations in all 4 bases. So here we have very strong correlation in the z and x basis, but no correlations here at all. So we need to make a state in which whatever pair of properties which we choose, red color of the first card, parity of the second card, there will be some correlation. Parity of the first card, parity of the second card, there will be some correlation. So we need to have correlation in all 4 of these possible measurements. And then we will see something that absolutely cannot be explained by classical world. Okay, how to do this? Okay, this is the last ingredient necessary for our program. So for this, we need to modify our state a little bit. Namely, I take this state, Bell state phi minus, and what I will do, I will rotate one of the qubit, green qubit, by 45 degrees, like this. So this is how this rotated state looks in Z color basis, and this is how it looks in X parity basis. So this is a state that will demonstrate properties impossible for classical cars. And to see this, let's consider what happens when we measure these two qubits, either in Z or X basis. Let's consider first case when we measure blue qubit. We measure blue qubit in Z basis. So we measure in Z basis, so I choose this part of the picture, this view in which blue qubit is drawn in Z basis. So I measure blue qubit in Z basis and say this qubit chooses state Z equals 0. So it chooses R of hat position. Then green qubit will also choose R of hat position. So after my measurement, say two qubits are like that. So I measure Z property of blue qubit and I get 0. So you can also consider all other cases, but well, it's clear that they give the same result because of the symmetry of state. Now, green qubit is not exactly at this position. So there is some probability that measurement result will give 0 and some probability that measurement result will give 1. But this qubit is much closer to Z equals 0 state. So I will get 0 much more often than I will get 1. You can work out mass, it's not that difficult using quantum formula, and this probability that measurement of green qubit will give 0 is cosine squared of this half of rotation angle. It's 85%, it's quite good probability. So we see, so in 85% cases, if I measure green qubit in Z basis, I will also get 0. So in 85% cases, measurement of color of my Z is a color, so color of my one qubit will be the same as color of the second qubit in 85% cases. Now look, this green qubit also is very close to this, to the line, to the point when X equals 0. So when I want to measure X, when I want to measure green qubit in the X basis, I will also get X equals 0 in 85% cases. So the color of the first qubit is correlated with parity of the second qubit. So it's like if first qubit is red, then it's high probable that the second qubit is also red, and it's highly probable that the second qubit is even. So there are correlations. So we see we have both correlation for normal Z measurement and correlation for ZX measurement. Now let's see what happens if I measure blue qubit in X basis. So I use this X parity basis picture. And let's say that this time, well, when I measure blue qubit, it chooses error of tail position. So blue qubit ends up at this X equal 1 state, and then green qubit will be here. So this is our state of the after measurement. And you see, so green qubit, blue qubit here it has X property 1. So if I measure Z property of green qubit, I will have 1 with high probability, with this 85 probability. So there will be correlation between X of blue qubit and Z of green qubit. But if I measure X property of the green qubit, I will get a result opposite to that of the blue qubit. So we have correlations like this. And I understand that it is difficult to follow through all these calculations of correlations. But you can look later, and well, this is a simple picture. It's just difficult to follow everything step by step. But you can draw this yourself and you can understand how it works. So this green qubit between X equals 0 and Z equal 1. So we will get very often these results of measurement. And this is related in such probability calculations to get this number. So this is where you need to get your mass. Okay. But this is the most difficult part. And this is a correlation table. And this is absolutely amazing correlation table. This is a correlation table that if you look at it and think enough of this, you will say that's impossible to have. And to show you why, let me redraw these correlations in a different way. So this is ZA equals ZB, ZA equals ZB, ZB equals XB, ZA equals XB, XA equals ZB. So this is psi. So I have here 4 correlation relations, and here I have the same 4, but I arrange them in a square. And this is impossible square, because this square has 3 signs equal and 1 sign not equal. Now think about properties of a qubit, like red, black, even, and odd. And you don't even need to think about any properties, because it's not even about physics. It's about logic. With this square, there is no way how I can satisfy all 4 sides of it at the same time. Because if XB equals ZA and it is equal ZB, it is equal XA, then XA must be equal XB. I can easily satisfy 3 sides of this square. I can choose 2 red even cards. Okay, so this is satisfied. Or I can choose 1 red, 1 black, but both even. So this will be satisfied. 3 sides is easy. But 4 sides, I cannot satisfy all 4 sides of this impossible square, because it's not possible just from logical point of view. Right? No matter what properties we are talking about. If A equals B, B equals C, C equals D, then D must be equal to A, and we have 1 side which cannot be satisfied. And what that means? That means that no matter how I prepared these quantum cards or real cards, if I will probe each of these, like if I have 2 objects, A and B, with 2 properties, Z and X, and I probe one of these equalities or inequalities randomly, I cannot get success rate more than 75%, because at the same time only 3 or 4 sides can be satisfied. So if you have some objects A and B, and you randomly probe one of the sides of this square, and see whether your result satisfies this equality or inequality or not, you cannot get success rate more than 75%, right? No way, just by mathematics. But look at these numbers. This is what quantum physics predicts. Quantum physics predicts that, well, for such rotated entangled state, correlation, so satisfaction of this size will be 85 in every case, for every side. So classical correlations in this impossible square, they are limited by 75% at most. You don't need to know physics. You need to have just elementary logic for that. And simply follows from our understanding of what properties mean, what equality means. Quantum, well, correlations are limited by 85%. And this is something that we can measure. We can create this state, and then we can randomly choose one of 4 measurements, and then we can see whether our correlations are above or below 75%. If they are above 75%, even by a tiny bit, that will mean that our universe is not real, that cards choose color and parity at the moment we look at them, that there is no point of talking about properties of objects without considering experimental measurements and how we measure them and so on. So let's do it. So here is, to do this I will use Python, and I will use Qiskit package. So this is a package developed by IBM specifically to talk to their quantum computers. So first I create quantum circuit. It has all the ingredients we considered during this lecture. Here I create Bell state phi minus, and then I rotate one of the qubit. So this is rotated entangled state. Then here I use two random drawing of quantum cards or random coin toss. Here I choose which side of this impossible square I will test in each particular run. So what measurement I will apply to card A and what measurement I will apply to card B. And finally, I measure these two cards. I measure them either directly. So here is this gate is applied conditionally. I applied this rotation gate only if here is 1. So if here is 1, I measure this qubit in X basis. I look at its parity. When here it's 0 and this 1 and 0 is random, well, I look at its color. I measure it in Z basis. So this is such a circuit. It's very simple. Now let me connect to the quantum to IBM quantum services. There are several quantum computers usually available. Okay, I will choose one. Usually there is quite a queue for each computer. I choose one which is least busy, so we will not need to wait for so long. And before sending my quantum circuit to real quantum computers, I need to compile it. It's the same that before a running program on your laptop, you need to compile it somehow. This is how compiled program looks like. So it replaces our simple rotation, simple gate that we were talking about by some internal command, but it does not change anything essential about this. Okay, and after we did this, so we can send job to processor. So now you see job status is queued. So it's sent to queue. So we have to wait for 36 hours, okay, before it will run. Usually it takes a couple of minutes, so we will see.
Do you have standard subscription, 10 minutes per month free?
No, this is a little bit better subscription, but okay, that kind of takes a long. I'm not sure if I have internet here. That may be. Because I am guest professor, and guest professors are not allowed internet. Yeah. Okay, I will run everything else, so it should. Of course, okay.
This last set yesterday night was maintained there.
Where?
On one of the computers, but you can see the like queue on the website.
Yeah, well. No. This is something with I think with Python. Let's do it again. Okay, so. Okay, I suppose there is something wrong with my internet access here because Python is not responsible. Okay, that's very bad because I wanted to run it live. But last evening, yesterday, I tried the same program in my home. So you see it's exactly the same the same program, exactly the same IBM Marrakesh quantum computer, exactly the same compile. And this were the execution results. Yeah, like you see, like Jupyter not responding, so it's I don't have internet access here, so I suppose like normal internet access. Okay, so these are the results that we obtained from quantum computers. So the first 4 corresponds to measurement result in ZZ basis. And you see here, these 2 first and last bar are very high. Which shows exactly the correlations that we expected. So here on this histogram, I simply color-coded correct correlations that we have and incorrect. So here we do not have 100% of course correlation in either case, but we have very large correlation. Visually it seems that correlation is very strong. And if we perform processing of the data, we will see that the correlation rate in this particular experiment was 79.5%. So for classical system, no matter what classical system we are talking about, this correlation is limited by 75% because there is no way we can satisfy 4 sides of the impossible squared at once. So 75% is at most. So here we have 79.5. It seems that there is a small difference, it's just a few percent. But well, the maximum we can get without any errors is just 85%. So we can calculate what is the statistical significance of this result. And this is more than 10 sigmas in this case. So so it's impossible to get the same result, well, just randomly. It's the same as you take a coin, you throw it, and it lands on its edge 100 times in a row. So this experiment clearly shows that, well, correlations that exist in quantum system cannot be explained by any classical model. So that they are that they can be described just by quantum entanglement and this quantum weirdness, and no hidden variable theory can explain that. Because it does matter what theory we think, like this impossible square, it's based simply on classical logic. It is not based on any specific theory. And therefore, by checking that like our quantum system violates this rule, classical rules of impossible square, we can throw out all classical theory. We can throw out our classical understanding of properties of quantum objects. Quantum object does not have properties by itself, or not necessarily have. Or they may be, so they choose properties like colors or parity at the moment when we measure them, when we look at them. Okay. Okay, and this of course is a very important result in fundamental physics, and of course real experiments with this type, real Bell tests, they were done with photons. They checked not just reality but also locality. So for this you need photons, and this is much more complicated than the things that I did today. But it's just like you can do this. You can run this program on a quantum computer. Everyone can. Okay, but the people, the pioneers who performed this Bell test, they received Nobel Prize in Physics 4 years ago, including Anton Zeilinger from University of Vienna. And their work was very important because, like, after this clear demonstration of violations of Bell inequalities, people started to consider, to look at entanglement differently. Because previously, during Einstein times, entanglement was a property that has to be explained out. So it's something that we don't know how to deal with. We can close eyes and don't discuss about this, or we can imagine some strange theory explaining it. But right now, it's not something we want to get rid of. It's something that we want to use. It's the most important resource in quantum computing, quantum sensing, quantum communications. Basically, everything quantum, everything that uses these quantum properties, they always use these strange entangled states. They always use these correlations which are strong as that any classical correlation can provide. And this transition is the most clear illustration of going from first quantum revolution, when we explain nature, to second quantum revolution, when we use nature as a resource and we use all the laws of classical and quantum world, no matter how strange they are. So with this, I will finish. Thank you for your attention.
Thank you very much, Vasil. Fantastic lecture. Very interesting. So you convinced us that entanglement exists. Other questions? And let me just start. You said that you started work with IBM quantum computer 5 years ago, and it looked very different. How many qubits were at the time, and what was the error?
7. 7 was at most.
Only 7 qubits?
Yeah, 7 qubit, it was, no, 7, when I started, it was 5 qubit at most. So it was like 5 years ago, the most powerful quantum computer only had 5 qubits. Well, I'm not sure, maybe there were some like in development probably were, but the ones that you can work had only 5 qubits. You can still make tests like this. With qubit, quantum processor with 5 qubit, but I tried it that time. I cannot do this because there are many measurements, and so error in each of these qubit was so much that well, this extra 10% of correlations, they all went into noise. So we could not do this. So right now, 5 years later, you can use computer with 150 something qubits. And you can do stuff like this and even more interesting experiments. Progress is amazing.
Yeah, you mentioned that there were other Bell tests of showing the Bell inequality. Are they also possible to do on these IBM quantum computers?
So first of all, yes, we can choose many different like Bell tests. For example, like I have this impossible square, equal, not equal. By choosing different quantum state, I can put this not equal where I want. Instead of z and x, we can measure in some other basis, because this is just like, it's important to look at from several points of view. There are also Bell tests that use different states. Of the states that I showed today, they are Bell states. They are simplest example of entangled states because we have only 2 qubits. There are very interesting Bell tests with 3 qubits and states, GHZ states, entangled states of 3 qubits. And one of the problems in second homework of my course in quantum mechanics ask exactly for such form of test. So there are many different Bell-like tests. So it was important to realize that we need to look at qubit not just from one point of view, okay, like heart is red or black, but look from correlations between different bases. This is where this quantum weirdness is hidden. And once you realize it, you can develop Bell-like tests very easily for any system of qubits, or even not something more complicated than qubits.
Thanks, very good talk. So you showed that the second quantum revolution, there has been all this progress on preparing entangled states, but there should be the alternative way of preparing the right measurement device, because if I measure in the Bell basis, then the zero state is already correlated. So do you think this is something that people should pursue, or is this like to fail?
What do you mean other way to measure?
So if I measure in the 0-1 basis, then all of these things are entangled, but if I take this entangled state as one element of my measurement basis, then I will never see correlations in this state, but I will see correlations of the simple 0 and 1 state. So I wonder if there is if you see a route on trying to, instead of preparing a state, preparing a device that can measure in a Bell basis.
Device that can, well, quantum computers can measure in Bell basis. So it's possible. So there are, I showed today two Bell states. Total there are 4 of them, and they form a basis. And if we have 2 qubits, we can write any qubit at superposition of entangled base states. And there are measurements in Bell measurements that can directly measure these states. We can realize this measurement with quantum computers. So this is a standard thing. For example, third lab on my course, Quantum Magnonics, students will teleport qubits inside a quantum computer. A necessary step of quantum teleportation, one necessary step is to prepare Bell state, and another necessary state is to measure Bell state. So it can be done with modern computers.
Yeah, so this Bell state experiment and Bell inequality showed that the maximum difference between a classical experiment and quantum experiment is like this 10% correlation. Is there other experiments with these Bell inequalities that would show higher inequalities or different ones, or is it always instead?
Like with this, with 2 qubits, it will be at most 85%, 85 something. 85, something like this. Okay, this is not so much. Oh, this is not so small difference. It seems like, okay, 10%. But I can ask you, like we have this impossible square. And we say 75% is when 3 sides are satisfied. 85% it means that there is some fraction when all 4 sides are satisfied, right? Which is logically impossible. This is what we see in experiment. And 85% that we see in correlation means that all 4 sides are satisfied in 40% cases. If you recalculate this. No. So it's not a small difference. It's a small difference because classically we can get 75%. So this is 100, but we are working only in this small region. So 85%, that means almost half of the cases we satisfy all 4 sides of the square, which is like, come on.
You said that we have 79%, this experiment you performed, and difference not 85 just because of error.
Yes, when you do this, you see, these quantum computers, they are very fragile devices. They undergo calibration every day, every 24 hours. Well, so every 24 hours, they switch off for maintenances. That's why they are calibrated, because all this rotation, all these gates, they have to be very finely tuned. Okay. And the percentage you get depends on the mood of quantum processor. When do you measure? So I got some correlations at 83%. There was, so probably it was freshly correlated processor. So 83 was the biggest that I saw. 79 is actually close to the lower threshold. Yeah. But it's still it's enough. It's important that there is more than 10 statistical deviations, like 10 sigma statistical significance.
And you said that this experiment doesn't solve problem of locality, yeah? So
Yeah.
because the qubits are nearby and so on. And that what Anton Zeilinger did with teleportation, does it solve issue of locality, or the teleportation over the longer distance is photon?
Well, teleportation is based on quantum stuff, but in teleportation we don't want to. Teleportation is another step in this way from first to second quantum revolution. In teleportation, we accept that this correlation exists as a given, and we use them to teleport. So of course this non-locality and this quantum entanglement is used in teleportation. It's like it's built into this. So teleportation is not designed to prove it. Okay, but there are experiments with photons when you can create entangled state of 2 photons, send 2 photons into 2 different labs, and measure them at 2 different labs. So and you can choose. You can make a random choice. How would you measure, like in Z basis or X basis? For photons, it's very easy. Z basis, it means horizontal or vertical polarization. X basis means diagonal, anti-diagonal polarization. So we basically need just to find polarization of photon. So you send them at large, like at 100 kilometers away. And 100 kilometers, you have several nanoseconds for light to travel through this, even several microseconds. Right? So you need to measure 2 qubits within these several microseconds, and then you will prove that these correlations are non-local.
But in order to exchange information, you're still limited by speed of
Yes, yes.
So how do they go around? Do they have super clock which are...
They just synchronize ahead. So they decide that, okay, like we will send like photon every second, and like you calculate how long this photon takes come to you, and you will measure one every second plus like 143 microseconds. I will measure 1 second every second plus 270 microseconds. So it's synchronization ahead of time. Because when you do this measurement, like you don't need to send information. We just, if we are 2 like 2 laboratories that doing this experiment, we will just agree how we will measure, and then we will compare our results. Yeah. Like post-processing is done afterwards.
Good. So if you no more questions, so then thank you very much once more.